Hi guys, I'm going to do a video like for this week. However, I'm going to do it little differently. I have already written everything that I wanted to tell you, and mostly this is a repetition of early chapters that we did for linear motion. Therefore, I think it is kind of straightforward to you all. So I decided to not to spend too much time there. Okay, so when I I'm using my green marker to draw lines, so please focus on my green pen. I am drawing a line from time to time. So over here you can see that the counterclockwise is positive, and here you have clockwise being negative, and it is going to be the case everywhere throughout the this chapter where rotational motions are discussed. And then the equation we discussed was S equals to R delta theta or theta in general, where you have the theta actually is the angular displacement. So we have that. Now the other equations that we have come across, they are the ones that are corresponding to the linear equations. So if you just look at the right word where I am circling here, linear motion, Vf equals to Vi plus At, all vectors, and delta x equals to Vit plus half At square, that's this one, and then Vf square equals to Vi square plus 2a delta x. So these are the three equations that we already know. And then the rotational motion, pretty much the same form. All what you are doing is you are calling velocity as angular velocity. So the first term here, angular final velocity equals angular initial velocity plus angular acceleration times t, and then the same form for the rest of the equations. And please keep in mind that the counterclockwise rotations are always positive and clockwise rotations are always negative. As a result of that, if you have a counterclockwise rotation, then you have these omegas, they are going to be positive values, and alpha is also, depending on the direction of its motion, can be positive or negative. So in other words, these are also considered as vectors. Now we defined omega as d theta by dt and alpha as d omega by dt. These two equations are also important because sometimes, as we discussed in the class, if theta is given as a function of time, in order to find omega, we will have to do a differentiation. Or if omega is given as a function of time, in order to find theta, we will have to do an integration. So please look at the notes. We discussed couple of those questions. Now there are a couple of additional equations. These are extremely useful because these are the equations that relate the angular terms to linear terms. So here you have the arc length, and there you have the angular displacement. So basically S is the linear form and theta is the angular form. And here you have velocity, linear velocity, there you have angular velocity. So this equation relates linear velocity to angular velocity. And the second one, I have a picture drawn to the right here that shows the tangential acceleration and the centripetal acceleration. Sometimes people call it AR as well. Anyway, A tangent equals to R times alpha, and A centripetal equals to V square divided by R. And then if you want to, now I am using my red pen, if you want to substitute for this V using the equation over there, that also can be done, and there you will get AC equals to AC equals to omega square R. That is also an equation for this. Now in order to find the net acceleration, we will have to take the centripetal acceleration and the tangential acceleration and use the equation that we've been using over the last couple of weeks. Actually throughout the semester this came out in different forms. So I'm going back to go with my blue pen, and this is the equation we are talking about. Finding the net acceleration is done by this formula, this equation. Now I'm going to let you pause the video and read this problem. A flywheel turns through 40 revolutions as it shows from an angular speed of 1.5 radian per second to a stop. And then assuming a constant angular acceleration, find the time for it to come to rest. Now there are a couple of important words here. Assuming a constant angular acceleration, this means alpha is not changing, alpha is a constant. And the second thing here, using the red pen now, finally the flywheel comes to a rest. That means final velocity equals to 0. And then initial velocity is given to 1.5 radian per second. And the question asks us to find what the time it takes, that's the first part, and the second part, angular acceleration. Now the equations that we need, and if you actually set up the table first, now look at this. The first one, angular velocity, initial value, final angular velocity, and the displacement, and alpha and theta. Those are the things that should go in the table. Initial velocity is given 1.5. Final velocity is given 0. Angular displacement is given as 40 revolutions, but revolution is not our unit. Therefore, multiplying this by 2 pi, we convert that into radians. There you have 80 pi radians. Alpha is not given to us. I don't know, it looks like a D. Let me see if I can rewrite it, and it looks like a little fish here. Okay, there you go. And there you have that. Alpha we don't know, time we don't know. Now let's turn to the equations that we have. These are the three equations, right? And the first two equations, if you look carefully, they both have alpha and t. So we can't use either of those equations because we don't know alpha or t. And having two unknowns in one equation, it is difficult to solve for one variable, right? So what I'm going to do is to use, what I'm suggesting you to do is use the third equation. Use the third equation, substitute all what you know and find alpha. So the answer to part B will be given by this. Then use the first equation to find t, and that would be the answer for part A. And then going back to part C, how much time is required for it to complete the first 20 of the 40 revolutions. So alpha, it was constant, we know that already, and initial velocity doesn't change for any reason. We change the delta theta from 40 to first 20 of the 40 revolutions. So we are going to use 20 revolutions and convert it into radians. That will give us 40 pi, and we are using this number and use the same alpha and find t. So you can use you know what, why don't you decide what equation to use there, and that would be the answer for part C. So I'm gonna stop here. This is a short video and I'm gonna upload it.